Beneath every ocean, continent, and city, Earth may be storing an astonishing amount of water hundreds of kilometers underground. But this is not a liquid ocean in a cavern. The water is chemically locked inside solid minerals. At these depths, water exists mainly as hydrogen bound into crystal structures, not as free-flowing lakes or seas.
The most important zone lies roughly 410 to 660 kilometers below the surface.
Geologists call it the Mantle transition zone, a pressure-built layer between the upper and lower mantle. This hidden reservoir matters because Earth's surface ocean and deep interior are part of one extremely slow water cycle. Water can travel downward with sinking tectonic plates, disappear into minerals, and return through melting and volcanoes. The difficulty is obvious. No drill can reach anywhere close to the transition zone. Scientists investigate this water indirectly, using seismic waves, laboratory pressure experiments, and rare minerals carried upward from depth. Then one tiny diamond inclusion provided the first direct sample from this hidden reservoir. To understand that discovery, first strip Earth into the layers pressure creates beneath our feet. The shallow upper mantle is dominated by olivine, a mineral with relatively limited capacity to store water. As pressure rises with depth, the same chemical ingredients rearrange into denser crystal structures. Near 410 kilometers, olivine transforms into wadsleyite, a mineral that can hold far more water. Wadsleyite does not contain underground droplets. It stores hydrogen inside defects in its crystal lattice. Deeper still, wadsleyite changes into ringwoodite, another high-pressure mineral with major water storage capacity. At about 660 kilometers, ringwoodite breaks down into minerals that generally hold much less water. That sharp drop in storage capacity can force water out and help create tiny amounts of melt. The transition zone may therefore act like a deep sponge, and, at its boundaries, like a water trap. But a mineral's capacity to store water does not prove the entire global layer is filled to that capacity. Because the transition zone is unreachable, scientists read its properties through the way seismic waves travel. Abrupt mineral changes at 410 and 660 kilometers create seismic discontinuities that geophysicists can detect. Seismic tomography converts thousands of travel times into images of faster, slower, colder, and hotter mantle. Their depth, sharpness, and local variations reveal temperature, composition, and possibly the presence of water or melt. Some low-velocity layers near the transition zone boundaries are consistent with small amounts of partial melt. Laboratories test that interpretation by recreating deep Earth pressures and temperatures in diamond anvil cells. When hydrous ringwoodite transforms under lower mantle conditions, experiments can produce melt between the new mineral grains.
Seismic observations beneath North America found velocity drops where mantle flow models also predicted downward movement across 660 kilometers.
Together, experiments and seismic data support dehydration melting as one way water may remain trapped near the transition zone. Still, seismic signals and experiments were indirect. Scientists needed a piece of the deep mantle itself. The crucial sample came from a rough diamond recovered near Juína, Brazil. Deep source eruptions had carried the diamond upward fast enough to preserve a mineral formed hundreds of kilometers below. Inside the diamond was a microscopic inclusion, too small to see without specialized instruments. X-ray diffraction identified the inclusion as ringwoodite, the mineral expected in the lower part of the transition zone. It was the first reported terrestrial occurrence of this high-pressure olivine polymine polymorph in a natural sample. Infrared spectroscopy showed that the inclusion was water-rich, in the mineralogical sense. It contained substantial hydroxyl. The preserved inclusion indicated roughly 1% water, locally, within the transition zone mineral. That was direct evidence that at least part of the transition zone is hydrous, not proof that the whole layer is equally wet. The diamond solved one question and sharpened another. How representative was that tiny piece of deep earth? A speck inside a diamond had transformed the debate from pure theory into direct observation. The discovery was widely described as an ocean in ocean inside Earth. But that phrase can be deeply misleading. The mineral stores water as hydroxyl, hydrogen bonded within the crystal, not liquid water filling open space. Hydrogen can substitute into defects where metal ions would otherwise occupy the structure. Each grain stores only a small fraction by mass, but the transition zone contains an enormous volume of rock. Across a planetary shell, even 1% water would represent a quantity comparable to vast surface reservoirs. Experiments show wadsleyite and ringwoodite can hold several percent water by weight under suitable conditions. If the entire zone were near saturation, its capacity could equal several surface oceans, but that is a hypothetical upper limit. The real mantle is almost certainly uneven. Wetter near some subduction systems, drier beneath other regions. Where tectonic plates carry hydrated rock deep into the mantle, local transition zone water may become concentrated. Temperature, iron content, mineral chemistry, and mantle flow all change how much water these crystals can hold. Water changes electrical conductivity, seismic speed, strength, and the way mantle rock deforms. Even when hidden inside crystals, hydrogen can make mantle minerals easier to deform over geologic time. That means deep water can influence mantle convection and the long-term movement of tectonic plates. The deep cycle begins when surface water reacts with oceanic crust and becomes stored in hydrated minerals. Sediments, altered crust, and hydrated mantle rocks can transport water toward a subduction zone. As the plate sinks, rising heat and pressure destabilize many water-bearing minerals. Much of that water escapes at shallower depths, helping generate magma beneath volcanic arcs. Volcanoes return part of the subducted water to the surface through magma and gas. But not all water returns immediately. Some hydrated material survives and continues much deeper. Inside the transition zone, wadsleyite and ringwoodite provide new crystal structures capable of storing that hydrogen. The result may be localized reservoirs shaped by ancient slabs, mantle circulation, and mineral reactions. When hydrated material crosses a boundary into minerals with lower storage capacity, water must move somewhere else. Some enters melt, some may migrate upward, and some can be recycled back into the transition zone. This is the deep water cycle, a circulation measured not in days, but in millions of years. Its pace is almost unimaginable, yet over Earth history, it can move enormous quantities between surface and interior. At the base of the transition zone, ringwoodite transforms into bridgemanite and ferropericlase. Because these minerals hold less water, the transformation can trigger dehydration melting. A 2014 study combined high-pressure experiments, seismic imaging, and mantle flow models to test this process. The observed pattern was consistent with partial melt forming where hydrated transition zone material moved downward. Even a very small melt fraction can strongly reduce seismic velocities and change how the boundary appears. If melt rises back upward, dehydration melting could help keep water concentrated inside the transition zone. Together, melting at both boundaries may create a long-lived geochemical filter around the deep reservoir. A similar release may occur when hydrated wadsleyite rises above 410 kilometers into shallower olivine stability. This does not prove a continuous global ocean. It describes mineral-bound water, possible melt, and a highly variable mantle. Every estimate of deep water depends on combining evidence that sees the mantle in a different way. Electrical conductivity can increase when hydrogen is present, but temperature, melt, and composition can produce similar signals. Seismic data also require interpretation. Slow waves may indicate water, melt, documentaries, high temperature, or chemical differences. The mantle is heterogeneous, so one region cannot automatically represent the entire planet. The diamond is direct evidence, but it is still one tiny sample from one locality. Even the diamond's source history depends on models of deep eruption, mantle flow, and mineral preservation. As a result, published estimates of the transition zone's total water content still span a wide range. New deep diamonds, better experiments, and denser seismic networks can gradually narrow that uncertainty. Future maps may reveal whether deep water forms broad reservoirs, narrow slab-fed zones, or a constantly shifting patchwork. The answer will probably be dynamic, because mantle water moves with a planet that never stops convecting. Water weakens mantle minerals, changes viscosity, and can redirect how heat and material circulate. That links deep water to plate tectonics, mantle mixing, and the generation of magma. Water helps rock melt at lower temperatures, making it a powerful ingredient in magma production. Volcanic degassing returns deep water to the atmosphere, where it can eventually rejoin rivers and oceans. Surface water then enters new crust, rides tectonic plates, and begins the journey downward again. The surface ocean is visible and fast-moving. The deep reservoir is hidden and geologically slow. Over billions of years, grevensed exchange between them may help shape the long-term stability of Earth's water budget. Earth's oceans did not evolve separately from the mantle. The planet's interior has always been part of their history. A planet's mineralogy and deep water cycle may help determine whether water stays at the surface, enters the interior, or escapes. For Earth, the transition zone may be a bottleneck that stores water and controls how easily it crosses into deeper layers. Its mineral phase turns pressure boundaries into valves in the deep water cycle. The story is not an underground sea. It is a planet-sized chemical circulation through solid rock. Its central reservoir lies in the Mantle transition zone, between 410 and 660 kilometers deep. Wadsleyite and ringwoodite can store hydrogen in crystal defects at concentrations far above shallow mantle olivine. A diamond from Brazil provided direct proof that at least one part of this zone held substantial water. But one local sample cannot tell us how wet the entire transition zone is. Scientists therefore combine diamonds, seismic waves, conductivity, experiments, and models to estimate the hidden inventory. The minerals may have capacity for several ocean equivalents, while the actual amount remains uncertain and uneven. What is certain is the cycle. Water moves down, changes minerals, and melting, and eventually returns toward the surface.
Even chemically bound water can influence the mechanics of the planet above it.
So the phrase "ocean inside Earth" is useful only if we remember what it really means. One reservoir flows in waves. The other is stored atom by atom inside rock. The next discoveries will come from smaller samples, better instruments, and clearer images of a world we cannot visit. The biggest question remains simple: how much water is actually moving through Earth's hidden mineral reservoir? The answer will reshape how we understand oceans, volcanoes, plate tectonics, and the long-term evolution of the planet. Earth is not hiding a sea beneath our feet. It is hiding water inside the architecture of the planet itself. That line connects rain, oceans, sinking plates, deep minerals, magma, and volcanoes across geological time. The familiar water cycle runs through clouds and rivers. The deeper cycle runs through rocks and tectonic plates. Deep storage can last far longer than any surface reservoir, even though the mantle itself keeps moving. Every journey through the mantle changes the mineral container and therefore changes where the hydrogen can go. That is why pressure, not empty space, creates Earth's hidden water reservoir. The reservoir is invisible because the rock still looks like rock. The water exists in the chemistry. A microscopic inclusion revealed a process operating across a layer thousands of kilometers wide. We know the mantle can hold oceans of water. We still do not know exactly how much it holds today. What lies beneath our feet is not a secret ocean. It is a hidden planetary cycle written into minerals. And that hidden reservoir may be one reason Earth has remained a water world for billions of years.